start off, our talk is called Thermoptic Camouflage. I don't know who here is Ghost in the Shell fans. Woohoo, Ghost in the Shell! Anyways, so we thought the whole thermoptic camouflage thing, Ghost in the Shell, was awesome. Basically, it's like sort of invisibility suit, and it was a good title for the talk because we're talking about how you can make exploits invisible to your standard IDS or IPS. Quick introductions.
Yeah, my name is Brian Caswell. I am a principal research engineer for SourceFire. We do an IDS, IPS, and we're the primary developers of the Snort intrusion detection product. I am a Metasploit developer and a member of the SHMU group.
My name is H.C. Moore. I'm Director of Security Research at a company called Breaking Point Systems. We develop hardware that makes other hardware scream, and that's basically it. I'm also the founder of the Metasploit project and also a lead developer. So the plan for today, basically show you how to do evasion at every layer of the stack. Start off at layer 2, do layer 3, layer 4, and then all the different application layer protocols, and show really where the IPSs and IDS products are falling down. Some of the demonstrations we had planned today aren't going to work as well as we thought because the appliance I was going to bring with me as our sacrificial lamb wouldn't fit in my luggage. But we'll have demos anyways, but it won't be quite as cool. So the quick thing about evasion. The whole principle behind doing IDS or IPS evasion is you have to know more about your target than the IDS or IPS does. Whatever product you're trying to evade, you have to know more about the system you're attacking than it does. And that's how you can do things where it sees one attack, but you send another attack. And that's just basically, that's the basic rule. If you know your network better than the IDS does, you do things like abuse routing issues and TTL and asynchronous routes to make sure that the IDS doesn't have a clear picture of what's going on. Also, if you know your IDS really well, you know exactly what signatures it uses, how it does pattern matching, and what its weaknesses are, and you can abuse those things to also bypass the IDS or IPS. So kind of the evasion layers we're going to talk about today are, first of all, hardware, layer 1, layer 2. There's really not a whole lot there, and what is there isn't really relevant these days for internet-based attacks. Then we're going to go into operating system layer vulnerabilities, where, not really vulnerabilities, but differences where fragmentation is different between different platforms, how you can abuse that. Some of that's rehashing, some of that's new. And finally, we're going to go into application layer attacks, everything from client-side security to DCRPC and SMB. First off, kind of layer 2 stuff. There's a lot of different ambiguities of the Ethernet layer. Depending on what card you have, it may drop a frame depending on if a certain bits are set or if the length field's too long, or if you have, multiple VLAN headers. It's all sorts of tricks you can do at the layer 2 level that'll cause an IPS to route the packet because it doesn't understand what it is, but may allow the target to actually process it anyways. And you can use things like broadcast destinations where the IDS won't process the broadcast or it will process the broadcast in a different way. There's lots of different tricks to use the Ethernet layer. We're not really going to go into it too much because at the layer 2 level, it's not really that practical. And even at a large organization, layer 2 attacks aren't that significant because you have to go through a router or a switch to get to your target.
The next layer up that we want to talk about is the OS modeling. The first people that really set the mark for IDS evasion was Paytech and Newsham. They released a paper a number of years ago. They talked about TTL evasion tricks. So if your TTL at the IDS, if a packet is going to drop dead midstream before it actually hits the host, what the IDS sees of the TCP stream is going to be different than what the host sees. They also talked about IP fragmentation differences between how they handle overlapping. Same thing with TCP fragmentation and then sequence issues. There's a number of other tricks that they talked about, different host and networking tricks, and then fake teardown sessions. So if you do fins mid-session that the host is going to ignore, but because they're off with sequence numbers, but the IDS will say, hey, there's a fin, I'm going to shut down the session. So the IDS thinks that the session is shut down, but the host doesn't. The host will continue on connecting that. That's kind of old history. So a little bit of overview of how fragmentation works. You take an IP packet and you split up into smaller chunks. So if an IP packet won't go across what the different network cards will support. So the minimum fragment size is 8 bytes. So each of the different IP stacks that are implemented all implement how they handle overlaps and duplicate packets and missing sections in the fragmentation differently. Well, one of the nice things is because they're all different, the IDS has to know what each of them do and how they handle it and how they handle each of these odd cases and put them back together so they know what the actual host is, when the data gets to the host, what's bad and what's not. And unfortunately, this is incredibly difficult, especially when the different versions of the different operating systems change how the fragmentation is handled. So not very long ago, Paxson and Hanley released a paper discussing a number of the different IP fragmentation models that were released. The popular ones they came out with, so they released a very simple model of how they handle that. So they send out 6 different packets. As you see them on the screen, they come in the order of 1, 2, 3, 4, 5, and 6. And these are overlapping and gapping fragments. So when you line them up, they're lined up so depending on how the operating system reassembles the fragments, they'll reassemble only into a chunk as big as a 12-byte chunk. So if we look at how BSD handles it, it's very simple. As the first packets that come in first, those are accepted, and then additional data is laid on top of that. BSD write, the same sort of thing, except if the data in a fragment that comes in afterwards, it contains a gap, they will overwrite where the gap is. In the same thing, Linux does something very similar to the BSD. And then you have Windows where it just takes the first fragment. It always takes the first fragment for any of the gaps that come in, ignoring everything else. At least that's what Paxson says. And then iOS handles it the exact opposite way. All the fragments that come in, they just handle them in reverse order. Whatever comes in last, they overlay that on top to get the last 12 bytes. Well, unfortunately, that's not exactly how it works. So the way iOS handles it now is overlapping fragments are just dropped, which is probably the best way to handle it. There's no ambiguity.
Ambiguity.
Yeah, that word. You shouldn't see overlapping IP fragments in a real-world environment. So iOS and Cisco decided, hey, this isn't supposed to happen. If you see it, just drop it, because it's not supposed to happen in the real world. So they handled it correctly. So a couple of the other models that they had were not quite right. So one of the things that's interesting to know that for BSD, the way that BSD write actually works is if the fragment ends at the end of a buffer that already exists, then it will overlay that. Will only overlay it if it ends on a fragment that's already existed. And then Windows and Solaris their models are slightly different as well. It will only do the overlay, or it will also overlay if there's a gap, but one of the fragments totally supersedes one of the previous fragments. So as you see here, normally what was previously thought is where the 3.3 would exist, that was already seen, so we'll accept that, and then we'll overlay 5 before and 5 afterwards. Well, what is truly happening, because the packet that comes across with the 4 5s, when that happens, it totally overlays on top of the 3, so those are overlaid and are just dropped. And there's a ton of different application modeling issues.
Okay. So one of the biggest things about application layer attacks and application layer evasion is for every single protocol out there, each vendor implements that protocol a little bit differently. Take something as simple as a web server, for instance. You do get/HTTP 1.0, and there's some spaces between the URL and your GET request and your HTTP version, and that's basically it, just starting with that. Depending on what vendor it is, they may treat space characters as a different character. And we'll get into that a little bit later towards the end. But basically, depending on how the application is written, what characters it thinks spaces are, what characters it thinks line delineators are, it'll handle that packet differently. So as long as you know more about how that application reassembles or actually processes the stream you send it, as long as you know more about that application than the IDS does, you can make sure the IDS sees something completely different than what the application sees. Vendor-specific extensions are a large problem because anytime you add an extra extension to a protocol, say with the LDAP stuff as part of Active Directory, or the funky DNS stuff, and Rendezvous or Bonjour or whatever it's called these days, depending on what the IDS vendor does, they may not be able to process those extra extensions correctly, may not know what to do with them, and therefore any vulnerabilities in that protocol are hard for them to be able to detect at a protocol layer.
Yeah, another example is, for example, if you have IIS installed, it handles directory normalization in one way. If you have the front page extension, the front page extension only mapped to a certain directory inside IIS and exposed in a certain directory on the website, only in that directory will it be handling the evasion, reassembly and the conversion of directories and as it's handled through the front page extension, but the rest of the website will be handled somewhat differently. So all of that has to be handled by the IDS, and most IDSs can't do that yet.
And just about every protocol out there, there's at least one trick you can play with. There's at least some trick you can do with it that, depending on what the application is, will handle it slightly differently. You want to cover sidestep?
Yeah. So the first real application evasion papers that were released was Robert Graham from ISS released Sidestep. It had a number of different IDS evasions and bypasses that he implemented. The primary ones that he discussed were SunRPC fragmentation. So at the TCP layer, you can fragment SunRPC requests. At the time, none of the IDSs actually had, except for Robert Graham's IDS, could handle that. Also, one of the interesting things that he also did was FTP. So everybody knows that Telnet has negotiation options. So what kind of terminal it supports, how does it handle backspace, how it handles tab, that kind of stuff. Well, FTP, because it's command line based as well, FTP also supported all of these Telnet options. So that was something else that he added in. So you could take a FTP login, add in the middle of my username, add in my escape character is this other thing. In the middle of the username, so the IDS has to understand that. He also added the HTTP URI encoding, so encoding a slash as the hex equivalent, encoding the dots as a hex equivalent as well. Again, there's a lot of very new techniques that we're going to discuss today, a lot of very vendor-specific URI encodings, some brokenness in the actual implementations of the protocols that most IDSs, if you read the RFCs, you're not going to, as an IDS implementer, you're not going to understand how each of the brokenness is handled. And then we're going to talk about some of the more deep protocols. And then we're also going to talk about some client-side attacks.
SMB, I mean, I'm assuming everyone here knows what SMB is, has heard of it before, that kind of thing. SMB is pretty basic. SMB is the basic, generic transport protocol used by Windows and used by Samba for everything from file sharing, system administration, user account management, all sorts of things. RPC calls, DCRPC, everything goes over SMB in Windows, in the Windows world for the most part. With the exceptions to that are the bare DCRPC protocols that go through their own wrappers. SMB-based vulnerabilities. If you're writing an IDS and you want to detect vulnerabilities using the SMB protocol, you have to look pretty deep. You have to look for things like malware propagating, like basically file rights with certain names and certain content. People actually accessing the registry service in a way that should be, looks like an attack. You have to be able to parse the registry protocol, which is actually a DCRPC application running on top of SMB. Authentication flaws, you see someone to log in with a username and a password that's usually used by a backdoor or installed as part of it, some kind of malware. You need to be able to decode the authentication credentials from the request. And finally, there's once you get into DCRPC, there's so many other vulnerabilities that people are looking for and you need to be able to detect if you're an IDS vendor that it becomes very difficult to correctly detect those attacks if you have to parse SMB, DCRPC, and so on. So if you're an IDS developer, what do? The basic way is you create a signature for it. Say, I want this string. This attack has this string in it. For example, let's say you're trying to detect the LSAS vulnerability, where it's an overflow in a DCRPC service. You're looking for a certain string that's part of the exploit. Well, that works great until someone changes that string or uses, TCP segmentation, DCRPC fragmentation, or SMB fragmentation, or SMB segmentation to bypass this stuff or do padding. That doesn't work very well. So then they go to state tracking and say, okay, what state is this protocol in? So I'm going to look for a signature in this packet, but only when the packet's in a certain state, like after the DCRPC bind request has been seen for this given UUID for this attack. And then they realize that doesn't work, because you can still do fragmentation, still do things to bypass it. Then they start doing state plus context tracking plus signatures. So they have to basically create an entire DCRPC state engine into their IDS to be able to properly track these requests and figure out where the vulnerabilities are. And once they get that deep into it, they become really application and operating system specific. If that operating system accepts some strange flag or works slightly differently than they think, you can still evade that signature. So the IDS vendors are really behind a rock and a hard place with regards to how to detect these attacks, but at the same time, all of the new attacks that we're seeing on the internet, like things like Blaster, things like the LSAS stuff that are being used by self-propagating malware, all of those use these protocols. So unless you can detect these attacks correctly, your IDS is basically worthless. So the IDS is basically on the end of a pointy stick right now, and we're going to have fun playing with them. SMB evasions, one of the nice ways you can do it is via segmented read and write operations. When you're doing a DCRPC transaction through SMB, there's like 5 different ways you can do it. You can do it through 3 different transaction calls. Each of those are slightly different in terms of how they're formatted. You can also do it via read and write calls, just straight open a pipe, read to it, and write from it, and use that to actually do transactions in that pipe. And when you're doing those read and write calls, when you're working on a pipe, you can actually write it out 1 byte at a time. So that's not 1 byte of the network, that's this massive SMB request in the network as part of a TCP stream, as part of an IP stream, but still only 1 byte of data towards the very bottom. And you can take your entire request, break it into 1,000 of those, and send it 1 byte at a time via TCP segmentation and read and writes. And unless the IDS is really doing really good state tracking, they can't follow that. One of the neat things about doing segmented read and writes is that when you're working with named pipes, the offset field doesn't matter. So if the IDS is smart enough to track what offset you're reading and writing to, we just randomize that crap. And they have to still figure that out. And they have to figure out whether you're writing to a pipe or writing to a file. If you're writing to a file, those offsets do matter, and you can actually write out a file via SMB using strange offsets and build the file out in the wrong order. And if you're looking for malware signatures or someone trying to write in a malicious file, that really becomes an issue with being able to track all that stuff. You basically have to create a complete copy of that file in memory before you can do a real signature on that. We're probably going to skip the demonstration on this just because it's a little involved, but we will go into it a little bit later. Another thing you do with SMB evasion is data and parameter padding. SMB is a neat protocol in that you've got this kind of static header at the top that then has a bunch of fields, and those fields are determined by the byte count. And the byte count determines what other fields are part of that packet or that request. The way that you determine where in that packet your data and your parameter fields start is based on a hard offset from the beginning of the SMB request. So you can actually write an SMB request where it tells of the data of the packet is actually in the header of the packet pointing back to itself. So you can actually create conditions where you have like a loop. If you're actually processing it by looking at the offset of something and trying to follow it, you can create weird conditions where you tell it to read outside of the packet and otherwise crash things and do strange things. And there's actually some unauthorized like memory leak bugs in the Windows API if you specify strange parameters for your requests. If you're an IDS and you set an offset to be beyond the end of the current TCP segment, in other words, you write like a 1,000-byte packet out and you say that the data for your packet is at the 1,001th byte, then the IDS not only has to look at that packet and parse the entire thing out, but then wait for the next one and read the first byte and assume that the first byte of the next packet is part of the current one and not part of a new request. So if you have a packet-based SMB parsing engine that actually looks at each individual packet by itself, you're absolutely screwed if you're doing IDS, trying to do any kind of IDS signatures with that. You can do really cool padding with that so that you can actually trigger, so since you can do padding at the end of the packet between the end of your SMB headers and your data and your parameter offset, you can make that padding interesting values that will cause IDS to freak out. For instance, you can pad it in a way that the beginning of the next segment center of the network actually looks like a completely valid SMB request because it's just your padding. You just make your padding start out with OXFF, SMB, and the rest of a fake header, and below that has some kind of like innocuous looking data, and then there's the rest of your attack that the previous packet's offset points into. So basically, if you're trying to do IDS with SMB, you're going to be SOL, and that's really it. Do we want to do demos and this stuff? I'm worried we're going to run out of time if we get really into the demos on this part.
We can come back to it.
Okay, we might come back to the demos depending on how we are in time. Metasploit actually has most of the stuff implemented already. So you saw the Metasploit 3 talk. Those options are already there, and you can play them.
There's actually only one of the SMB evasions that we're going to talk about today that's not implemented yet.
And this is this one. The echo command is really cool in SMB. SMB has this concept called echo, which is just you send an echo and it echoes it back. So if you want to trick the IDS into seeing something that happened or that the server looks like it replies back to, you can do an echo request with the request parameter bigger than the MTU. So the segment, it actually has to break up that request across multiple segments. So if you send an echo request for a really large value that it goes right to the MTU, followed by some data that looks like the beginning of an SMB response, then when that data gets echoed back to you, you get the first reply back with some data, and then the server replies back with an entire SMB response that's really part of echo data, but if your IDS isn't smart enough, it'll look like an SMB response to something that was never sent.
Right, a great example of using that is for the DCRPC bind. So you do a bind request, and then you do an echo saying, no, the bind failed. So you get the IDS will see the bind failed response, and then go, okay, I no longer have to track this handle ID because the server said, no, you weren't allowed to bind to this. And then the next packet that, you'll also, so the IDS state will be different than what the operating system will actually have.
And a lot of the attacks are based on the state of the IDS itself and how well it can track state. The key point in that is if the IDS doesn't track state, they can't do anything. None of these attacks are really relevant because there's so many other ways to bypass IDS. We're not even going to bother talking about them. You can just do things like TCP segments and other kind of like lower layer protocols to get around these things. Sorry. If anyone's ever looked at an SMB packet capture of a transaction, you'll see the string looks like /pipe in the packet when you're doing any kind of transaction on that pipe. That /pipe string doesn't really matter. You can make that anything you like. And a lot of signatures only look for that /pipe followed by the pipe name they're looking for. In reality, you can make that, hello, my name is Bob if you want to. It doesn't really matter. And you can actually, pad that out with any string you like or make it random or push it past the end of the MTU. All sorts of things. Do you have anything to add on that? Sorry. Yeah, same thing applies for state engine attacks. You can use that to push things past the MTU and fake responses and fake requests. I'm sure everyone here is familiar with the Unicode attack for IIS. That was like the best exploit ever. You just like type something into a URL and bam, you get command execution. The way that worked is you're actually passing a Unicode character set that the operating system treated as a valid file path for .. but the web request didn't see that before it handed it off to the API. You can actually use the same types of techniques to obfuscate any path name that's part of an SMB request. So every one of those Unicode ambiguities in terms of how it parses the path or how it processes it or using Unicode character sets for path names, they all apply to SMB attacks as well. So if your IDS only looks for a certain string and a certain path name using the standard ASCII character set or the Unicode but using UTF-8, it won't be able to detect the attack if you re-encode that path name. You can also pad out those paths with things like slash characters, any other valid path padding, any other kind of like Windows path padding or Windows path attacks apply to every SMB attack for the most part. But it just gets passed down to the same Win32 API that parses the path. Not too many folks have seen the non-Unicode versions of a lot of the newer requests because all the tools out there right now make everything Unicode. But if your signature looks for, say, a username and a packet, and if you're expecting Unicode, you'll see, first byte 00, next byte 00, second byte 00, third byte, and so on. But you can make that, ANSI instead of Unicode by setting a flag in the header and not actually have those null bytes in it at all, or make it Unicode but use a different character set and so on. So a lot of folks will actually write a signature for the Unicode version of an attack, but not for the non-Unicode version of the attack, allowing another way to bypass it. Anything you can do with SMB is actually chain transactions. You can actually do things like log into the system, open a file, read to the file, write to the file, close the file, and log off, all in the same set of packets. And you can just stick one transaction after another in a row in one giant pile of data, and then send those to the system in whatever order and whatever TCP segment stream you want, as long as they get reassembled back on the far end as being...
right, as in one single SMB request.
Right. And the neat thing about index chains is if there's an IDS that does a really poor job of following index chains, basically, and inside every SMB request, there's an optional field called index and index offset. That can either point to, if it's OXFF, just 255, basically the byte value, it means there's no more entries in the chain. If it's anything else, it means yes, there's an entry in the chain and it's at this offset. So if you're trying to process SMB requests, you have to follow that offset into the packet or into the next segment or wherever it is in the wire and figure out what the next SMB request is. However, you can actually make that offset point back into the beginning of the packet, actually point below the current packet. So if you're trying to screw with an IDS, you can actually make the offset to the next SMB request, point to the one above it, and try to put into a little loop and see what happens. So there wasn't one IDS that was vulnerable to that for a week or two before we contacted the developers, and it's already fixed. But.
And just so you know, for your IDS developers in the network, Microsoft is the only people that actually do the index chains. All the other SMB implementations don't do index chaining, and they only do 2 index chaining. So you can cheat the way that we cheat and snort is if you see more than 2 index, then somebody's trying to screw with you.
Or using Exchange, right?
Well, yeah.
Exchange is like breaks every single rule for SMB and DCRPC as far as doing really bad things and using strange features. I've seen chaining at me. I've only been 2 requests though. One of the kind of fun bugs that we found when I was working on the Metasploit SMB implementation is that the way that our socket implementation worked, it would actually end up getting nagled in terms of we'd do 3 or 4 sends, but they'd actually get pushed in the same TCP stream and sent all at once. And because they're all piled one after another in the same stream, and the offsets didn't start at the beginning of the packet, things like that, there's a certain IDS out there that wasn't able to process those. So they had to start doing full state tracking and look at every packet and whatnot. So if you're expecting the SMB header to start at the beginning of a TCP segment, it doesn't have to, and it probably won't, at least if you're using Metasploit after this. A little bit about DCRPC evasion. Does everyone know what DCRPC stands for? Okay, I forget too, so not a big deal. But DCRPC is basically the protocol used for all remote API requests in the Windows platform. If you're doing distributed comm also goes over DCRPC. So if you're looking at DCOM attack, DCOM is just an extension of DCRPC, and you can actually connect to it in many different ways. Over TCP, HTTP, UDP, SMB, a bunch of different ways via SMB. And there's all sorts of different ways to represent that DCRPC data, depending on what flags you set in the header of the request.
Yeah, one of the great parts of it is the large number of different ways that you can represent the data, and all the large number of ways, the different transports that happen. So when you look at the different IVS evasions, you can handle all the different numbers, all the different strings are all different, and then all the different string handlings are all different. So all the different strings can be in Unicode format, while all the Unicode evasions that we've all talked about, those are all supported in DCRPC as well. And then you can fragment DCRPC requests. And then so when you add all these things up together, an IDS is either going to have to implement thousands upon thousands of signatures, or have a gigantic state machine. And oh, by the way, the Samba implementation of DCRPC handles a number of the strings differently. They don't handle, or they don't have many of the brokenness for how they handle Unicode strings. So they're very strict about their Unicode strings. So you have to know what the actual target server is for inside of DCRPC, which is great for when people are doing proxying. So if you think the end host is Windows, it's actually not. Sometimes you can do a DCRPC tunneling over HTTP to connect to an endpoint that's actually running Samba, even if the proxy is running on IIS. So you say, hey, that box, I check the IP stack says, hey, that's Windows. Well, if they're doing DCRPC proxying over HTTP and the endpoint that they're actually talking to is Samba, then you have to know that as well, which is another great way to bypass IDSs.
This is actually the one use I've ever seen for the EBDIC protocol decoder, or the EBDIC decoding that's in Ethereal or Wireshark, whatever it's called these days. If anyone's ever seen that, when you go to Ethereal follow stream and you want to decode the protocol, there's an option for EBDIC, and that's actually a use for it, is that you can actually decode DCRPC requests.
Right. And how many of your IDSs, when you're typing in your signatures, you can write EBDIC strings? None. So the basic how DCRPC works, you connect to a transport. So you either you connect to a socket, or you're on SMB and you say open up this pipe so you can connect to a service. Then you say I'm going to bind to a UUID. A UUID what a specific service you want to bind to. So you say I want to bind to this UUID and this version of that service. And then you say I want to call function 4, and then you pass a bunch of arguments. So the basics of how it works. All the encoding of how the data is being transferred is all handled by the client, and it uses what's called NDR for encoding of all the data. So one of the great things that you can do is you can do, in the actual bind request, you can say, I want to bind to these 500 services. And most of the DCRPC implementations will process all of them. And if one out of the 500 works, they'll say for the 499, hey, this one failed. And then for the 500th one, it'll say, okay, this one is acceptable, and give you back a handle for that. So you can make your packets incredibly big and make the IDS have to track state for 500 bind attempts, all in one request. So one of the other great things you can do is you say, you connect to a service, you get a valid handle back, and then you can do what's called an alter context. So you say, I'm connected to service A. Then you say, hey, wait a minute, I want to take my same handle and make it so I'm actually connecting to service B. So you do an alter context, and you convert your session from talking to service A to service B. And then you can also do things like you can bind with authentication. Most of the IDSs, for their first rounds of implementation to DCRPC, didn't realize that there was an authentication flag. There's a number of different authentication mechanisms you can do on top of DCRPC, and they're all different in length values. And a number of them have issues in terms of implementation where they handle bogus data. So it's something else that they had to add just in to handle binds.
It doesn't matter whether you actually have valid authentication credentials or not. You can still use those authentication fields to pad out your request, and it doesn't really matter if your authentication fails. You can still actually work with the object when you're done.
Right. If the object is able to be accessed anonymously, yeah. If your authentication is bogus, it doesn't matter. It doesn't even bother to check. It just drops it. So the same, you can do a number of different things with the DCRPC calls to do evasions. So like I said before, you can fragment your DCRPC requests. So you can send 1 byte in time inside of your actual call. So you would say, I want to call function 1, and you really want to send 1,000 bytes of data. But you can send them 1 byte at a time and do 1,000 actual DCP calls, but only be 1 call request. You can also do something. You can also encrypt your requests. Supposedly, David Tell has released encryption for his DCRPC implementation. I haven't actually seen it yet.
It's actually, the encryption mechanism is already part of the InPacket library released by Core SDI. So if you go to like corest.com and click on like the open source link, you can find a DCRPC implementation that already uses the crypto stuff, the packet privacy stuff. So if you're worried about people not implementing this in their exploits, all the major exploit engines will have it really soon, if not now.
Yeah. And then one of the other things you can do is, so in your request, you're sending what's called a stub. So the structure that you're sending across the wire, you can append a lot of junk data in it. And each of the different, in a number of the different fields, they have my data is actually at the offset of 4. So in between where your actual value is, for where my data is and your data and your actual data, you can pad that with a number of with junk. And then at the end of your DCRPC request, you can append as much data as you want, and the DCRPC engine will just ignore it. Your IDS might not. And then one of the other things that you can do is you can also do, Microsoft added something they call an object ID. So normally what you do is you bind to a handle, You take your handle and you do a call on that handle. Well, they added what was called an object ID. You could say, instead of calling to this handle, I want to actually do this call on this specific object, and it's a UUID that's sent across the wire. Normally, the way it happens is that object ID is a UUID of the service that you're talking with. Well, in all the services that are implemented today on Microsoft Accept Exchange, that object ID, even if it's provided, is ignored. So you can pad out another 16 bytes in the packet of random crap, or something that you actually wanted to, to make the IDS say, hey, this is not an exploit, even though it might be.
A side request, a side effect of the NDR stub and being able to append data to the end of it is that NDR, anything you put into the stub is calculated as part of the length field of the DCRPC call, even if the program you're talking to doesn't decode that part of the stub. Where that matters is if you're doing an exploit for DCRPC service and you want to stick some shellcode into it, but you don't really have enough room for your shellcode, just stick 4 megabytes of shellcode at the end of your DCRPC request and it works fine. Just put it at the end of your regular stub data. It gets sent across the wire. It's usually pretty close to your regular stub, and just tell it to jump, 1,000 bytes forward, and you're going to land right in your NOP sled and the rest of your shellcode. So it's a really easy way to basically put unlimited shellcode into any DCRPC exploit just by appending it to the end of the NDR stub data that's never decoded by the application. So,
oh, and if your IDS requires you have the whole DCRPC request before you can process it, not only do you have to track all of that, you also have to track it inside of SMB, and then inside of TCP, and then inside of IP, all of which can have fragmentation.
Fragment, segmentation, out of order, everything. So it's a fun times.
It's a nightmare. And then the other thing, like I said, DCRPC has a number of different transports. You can do RPC over HTTP via proxying. Like I said, you can take an RPC request over IIS has a feature where you can proxy DCRPC to a DCRPC server. Normally it's implemented as locally, so you can expose DCRPC services via the web. Well, you can also expose RPC services inside of your network, so simple proxy servers. This is all done via using the UDP version, but you can also do this over the UDP version of DCRPC, which is a DCRPC version 4, but you implement it over TCP over HTTP.
If anyone remembers the old messenger overflow, the UDP-based one that Shock and I'm spacing on the name. Basically, there's this great demo of a UDP-based exploit that was demonstrated at CanSec West a couple years ago. Oded Horowitz. They did the demonstration on that. Basically, they had a single UDP packet that would trigger a heap overwrite that they did one at a time over and over again. And the way that Microsoft fixed the vulnerability is by basically disabling the entire UDP interface for that service. That was just one service out there. There probably the overflow occurred when it processed UDP requests and not when it processed TCP requests. So there may be other services out there that only bind to UDP that you can also find vulnerabilities in just by attacking the UDP interface only. But kind of a side thing, sorry. So the way that if you have a name pipe and you're trying to bind to it, like let's say you're trying to talk to a DCRPC service, that service is part of a certain process. That process has a name pipe, and you can talk to that name pipe via SMB. That's the normal kind of chain from getting to a certain process on a system through SMB from the outside world. So you connect to SMB, you authenticate, you open a handle to the name pipe, then you bind to the UID of the service you want inside that process, and then you talk to and do your requests. In the Windows world, a lot of services actually share the same process. And they share the same process and they share the same name pipes inside. And the way that the RPC implementation works in Windows is any one of those name pipes that are part of that service, if you can bind to any of those pipes anonymously, you can attack any one of the services that are part of that process, regardless if they're part of the same service internally. Kind of convoluted, but basically, if a good example is the browser pipe. The browser pipe is part of the browser service. The browser service runs in process with 5 or 6 other services, a lot of which have had vulnerabilities that have been discovered in the last couple of years. You can exploit nearly all of those DCRPC attacks by first binding to the browser request and not binding to the browser pipe, not to the pipe that you normally would, like NT services or workstation, and then actually getting to the service through that other mechanism, through a different service in the same process. So if you expose any pipe that has anonymous access inside the process, and you've got other threads in that process that also do RPC calls and expose an interface to it, all of those interfaces are not exposed to anonymous users as long as there's one way for an anonymous user to access that process. So kind of a bad description, but.
All right, so one of the things we were talking about is for how do you handle strings. So let's show you how NDR handles encoding an ASCII string. So the way it works is you send a length. So first you have to set the type of numbers you're sending. So is it big endian or little endian? Normally it's sent in little endian. So you set I'm sending 5 bytes. Then you send your offset to your data. Most of the time it's sent as 0, but you can also increase your offset and add in additional junk. And then you send your total length of your data. So if you have an offset, you increment that as well. and then you null pad your data to the 32-bit boundary because NDR is designed to be more portable. And then you're supposed to use nulls for the rest of your padding. Well, one of the interesting things, a number of IDS is still currently broken for, is they look for nulls for the padding. You don't have to use nulls. You can just use random junk. The actual end host will say, I'm supposed to read 5 bytes, and then the rest of it is just junk and ignore it. So one of the other things that's interesting, a couple of different issues is how you handle sending the empty string. So if you're going to send a null. So normally the way you would think it would work is you send a length of 0, then say the offset of 0, and the total length, well, the 0, and then the string of 0. Well, if your string is nothing, then to pad it out to the 32-bit boundary, you need 4 bytes of null. Well, a number of the services implement sending null strings this way. Well, a number of other services in DCRPC land will just send 4 bytes of null, saying, hey, my length is 0, and just skip it. So you have to know which version of the middle compiler they used to know how they're marshaling a null string, because most services you're not actually going to expect seeing a null. So the developers never hit the differences between the different middle compilers. So one of the great things out there in DCRPC land, for a long time, IDS developers didn't really understand how NDR or DCRPC worked. So a great example of that was when Blaster came out. How many remember reading the Blaster exploit? Okay, so like 10 of us. It was really awful. It was a great big massive junk of hex, and then a bunch of guys, their exploit, what they did is they just changed they changed all the lengths in the blob of hex when they inserted their overflow. They went back and fixed all of the offsets inside of the packet. Well, so one of the things that IDS developers did, so how do they look for this? Well, the Blaster was using a DCOM request. Well, so one of the things they did is each of the different objects that are sent via DCOM is marshaled via a meow prefix for each of the objects. So all the IDS vendors said, hey, wait a minute, we're not supposed to see DCOM. Let's look for the meow string. Well, if you actually look at the actual implementation, the meow string is just there for padding. You don't actually have to say meow. So the DCRPC implementation that's in Metasploit just sends random junk for this. So the great thing, the actual vulnerability was in an overflow in a path. So what you do is you look for // and then a really long name and then a slash. That's, the actual end vulnerability was that. Well, the great part was there are 8 objects in the request. The 7th one is the bad one. Well, the 7th one happened to be processed first. So in the previous 6 objects that were sent, there was a large amount of extra data that you could add. If your IDS was a first pass out, so if you saw a directory and the first directory that it saw was too short and it dropped the packet, you could evade the IDS. Evaded a lot of IDSs at the time. It still evades a couple IDSs as today. So the great part, and then a number of the different objects had strings that had an unlimited size. So you could send over a meg of data in a specific object and push the IDS into a state where it has to track way too much data, and most IDSs at the time would just drop the request. And again, because it was the vulnerability, like we said, was for paths, for an overlong path, all the different path vulnerabilities applied. So the Unicode vulnerabilities we're going to talk about in a little bit, the adding the // and then the triple slashes and all that other stuff, all of the IDS, those all had to be taken into account as well before the overflow happened. So the IDS had to take care of all that as well. So all right, so we're going to go into some additional protocols, some text protocols. So one of the things that's interesting is what's called header folding. So a number of the protocols out there today, HTTP, SMTP, iCal, actually emails themselves have what's called header folding. So if that header line is going to extend beyond what should fit in a normal terminal, the developers, what they're supposed to do is break it up into multiple lines. Well, a number of different applications handle how they break apart the lines and how they put them back together differently. There's a couple of broken email clients that send what's supposed to be the header, evil header, and then what you see on the screen, the bar biz foo. What they're supposed to see is that. Well, you can send a couple of the different email clients actually send the same, to send that. They break it across and make it look like what's on the bottom. So if you note, the first one is totally broken. There's no Z in the biz. So there's a number of different implementations of clients and the resulting servers that just handle the header folding just wrong. and how they reassemble those back together. So how do you know what your application does? Well, you have to test each and every version of, and how they handle them, and including how they handle new lines and spaces inside of the header folding. I guess we're going to go ahead and talk about some client-side attacks. A large number of vulnerabilities that are coming out these days, thanks to HD and the browser of the month, browser bug of
Month of browser bugs, I guess, was the name of the topic. So the name of the blog.
There are a bazillion bugs in web browsers and local mail clients and MP3 players and whatnot. So how do you handle this? How do you make your IDS handle that? How do you handle each of the different versions of IE and all the vulnerabilities? Well, there's no real firewall. There's so many ways to do lots of different evil things. We're going to talk about a number of the evasions that really most of these, the IDSs can't have, have no way to solve these problems. So the first one is Unicode. So HTTP, you can Unicode encode all of the data that's sent over HTTP. So all of the HTML exploits that HD released last month. So you can encode them. There's a number of different UTF encodings. So UTF-16, both in Big Endian and Little Endian, and UTF-32 again in Little Endian and Big Endian. And there's also a couple others, UTF-7, UTF-8. We'll talk about those in a minute. Normally the way you do it is you send a header with a content type, HTML, and then a char set. Which character set are you going to use? Which version of Unicode are you going to use? Well, the great part is a couple of different browsers, not all of them support if the first 2 bytes in the packet are an invalid character set. So FEFF will say it'll force it to use, say, the rest of this document is now UTF-16 Big Endian. And so without sending the content type, you can force, the browser will know, hey, process the rest of this request as UTF-16 Big Endian. A number of the IDSs don't handle that yet. All right, we'll talk about UTF-8. So UTF-8 has a number of different evasions that you can do inside of that. So there's a large number of ways that you can encode the letter A. So normally you would encode it, you can just say A. You can also hex encode it of 41 with an overlong encoding like what was vulnerable with IIS a while ago. You can also say C1A1, which is a valid overlong encoding. For each of you can actually encode it up to a 6-byte long encoding. Well, for each of the 6 bytes that you can encode it for an overlong encoding, there's 2 bits that are ignored in the actual processing of the decoding of the character. So you can make them be random junk. So example, to do an overlong invalid encoding, you can make A be C121 or C161 or C1A1 or C1E1. I'm not even going to go through the 3-byte. There's also, you can do 3-byte, 4-byte, 5-byte, and up to 6 bytes. So really, there comes out to be, for just the letter A, there's 125 ways to encode A if they're using UTF-8. What's interesting is not all the browsers handle UTF-8 correctly. Some of them handle a number of the valid overlong encodings. Some of them handle invalid overlong encodings up to a certain size. Some of the versions of IE support overlong encodings up to 3 bytes deep. Some of them support up to 6 bytes deep. So again, what the browser supports and what the IDS support, you have to handle all of those.
And with client-side encoding, there's also a difference in terms of, this isn't really an IDS and IPS problem so much as it is a general problem with anybody trying to do malicious code detection. What you'll notice is the malware, the antivirus, the IDS, the IPS, the WebSense, all these different companies are basically trying to do the same thing these days. There's so many client-side attacks that everyone who's doing client-side attack detection is kind of going towards the same point, which is being able to decode any HTML page, have JavaScript virtual machines, all sorts of things, trying to figure out whether an attack is really an attack or not in a web page. And all these different techniques here don't only apply to the IDS, they also apply to things like your antivirus looking for an automated malware install as you browse the web. So this goes a little bit further than IPS in terms of the impact for this and the folks who really need to care about it.
Yeah, and again, this makes it great fun for cross-site scripting things. So we're going to talk about some of the different JavaScript evasions. You should all recognize the first one. Say, I want to embed the string evil into my HTML string. So there's a number of different ways that you can do that. You can add it with an onload. You can say, onload, do this JavaScript handle. So you can do if you write an IDS string that actually looks for evil, you can do something you can do what's called unescape. So take a hex string, unescape it, and make it the regular ASCII string and insert that into the HTML. You can do a number of different things that cross-site scripting type attacks. You can say, make this JavaScript happen inside of a font tag. So set up the background as a URL, which the URL evaluates to some JavaScript.
The ECMA script spec also allows unescape with the %u stuff. So when the IIS vulnerability came out, people realized that, hey, you can do encoding with %u, byte value. And like, well, why does this work? This isn't part of any HTTP spec. This isn't part of any URI spec. But it is documented in the ECMA script spec, which is what defines JavaScript and JavaScript-like languages. %u is nifty because depending on what the endianness of your platform is, it'll decode to a different thing. So for instance, on the x86 and little endian platforms, if you do %u 01, 02, that actually becomes 02, 01. But if you do it on a PowerPC system, that ends up becoming 01, 02. So depending on what system you're on, you can use unescape with the %u sequences to decode it differently and confuse whatever the IDS or anything that's parsing that HTML file.
But additionally, some of the other ways that you can do that. One of the great things about HTML interpreters, they try and, there's a lot of people out there that are writing HTML that have no idea how HTML actually works. So they do a lot of things to make it so web pages render the way that you think it's supposed to, even if it's not totally correct. So you can add spaces inside of your JavaScript. So you can say JAVASC script. So instead of actually saying JavaScript, it's all broken up with spaces. Also tabs and new lines also work there as well. Your IDS has to handle that too. One of the great things is, so the same thing that we said before about inserting the invalid characters, the FFFE, or the FEFF, which says, hey, this is UTF-16 big endian. Well, if you embed a number of browsers, if you see that at all, it just removes them. So as it's transferring across the wire, you're going to have FF or FEFF. But when the browser interprets it, it's going to say, hey, that's an invalid character, just drop it. And then, so like you said, if you embed it inside of a script tag, well, when it goes across the wire, that doesn't look like script to any, to any normal, person looking at it or an IIS looking at it. But when it's evaluated by the browser, it's going to say, hey, that's a script, and do an alert. So one of the great things is, so people are doing things like for prevention of cross-site scripting. They're evaluating and saying, remove where you see script. Well, one of the great things is, so most people are using PHP for that, or Perl or whatnot. A number of the different regular expression engines, if they are compiled to support Unicode encoding, which most of them are not compiled by default to support that. If they are compiled to support that, the Unicode encoding is somewhat broken. So if a character set is invalid, it'll just say, it'll stop processing and just return back as okay. So you get into if you add, FF or FE inside your, into your form field that you're submitting, when it's submitted, and then the regular expression tries to remove all of the stuff, when it gets to the FF or the FE, it'll just stop processing and say, okay, the rest of the string is okay, return it, and then when it's and then the application continues to use it thinking it's safe because it passed it through its perfect regular expression. So one of the other ways that you can hide stuff in web browsers is you can encode things in base64 and include them as an object inside of an object tag. So the example that we gave here is is a base64 encoded string of evil text. One of the things that the IDS vendors are having a problem with is they don't want to implement a base64 decoder in line. Well, unfortunately, they started writing signatures for the base64 encoded stuff. The problem is, so the string foo, well, in HTML land, spaces are pretty much ignored. So foo and then foo prepended or appended with a space or new line or whatnot are encoded differently in base64. Well, unfortunately, a number of IDS vendors are implementing signatures for base64 encoded attacks. Well, add a space at the beginning of your attack, the entire encoding is now wrong.
A little bit about compression issues. There's actually a IDS recently added support for HTTP compression as part of their decoding protocol, and we won't get into it too much, but we did test them with what's called the zip bomb. Most people are familiar with this as being, a zip file that's a really small size. When you expand it, it becomes this multi-gigabyte file that chokes up your system. And it's a fun attack against things like SMTP gateways, things like that. This also applies to things like HTTP requests, though, and HTTP responses, because you can do gzip encoded responses for all HTTP replies with HTTP 1.1. If you support transfer encoding gzip, which most browsers do these days, you can gzip encode the entire page and set it all down. And unless the IDS knows how to decompress all that and decompress it in a way that you can't abuse it, eat all memory, and otherwise cause it to throw an error, you can bypass any signature in that.
Right, and the great part is if you're using gzip for the encoding, you can also in the gzip header, you can add two different fields that are arbitrary sized. They're just null terminated strings that in most gzip implementations, and if you're decompressing live, it just drops that data. It says, hey, this is a string, just ignore it. Well, so you can, if your gzip implementation, like a number of IDSs have right now, they don't support the name or the comment field, so you can append a bunch of extra junk, make them decode it, say, hey, this is an invalid decoding, and drop the packet then. And even worse, there's 3 different compression algorithms that the browser supports. There's gzip, deflate, and compress, which I can't remember if it's deflate or gzip, which are the same actual decompression, but they one of them doesn't have the gzip header. And unfortunately, a number of IDS vendors are doing something wrong where they're actually writing signatures for the gzip, the actual result of the gzip encoding. Unfortunately, there's enough for most of the compression algorithms support different levels of compression, so that adding if you're using the command line gzip interpreter, you use the gzip-9, compress it as much as possible. You can also do a gzip1, and the gzip signature will actually be very different.
Good examples in the Metasploit WMF module, we changed it so that it sent 1 byte at a time in different chunks, with each single byte being part of a total compressed body of a randomized WMF file. So the IDS vendors had to, think a little bit about how to decode this stuff, and unfortunately, they all picked the wrong approach to detecting it, which is to look for the static compressed data sent 1 chunk at a time, which is silly because as soon as you change the default options, it no longer works.
Oh, one of the other great things you can do for all the different browser attacks that that have been released lately, but you can also encrypt them. Well, there's a number of ways. Everybody knows HTTPS exists. There's a number of ways you can do that as an evil person. When you can purchase a certificate. I, for one, when I want to attack somebody, don't want to buy a certificate. Those track back to a person. Most of the certificate authorities out there that are require a photo ID, a passport, or a valid business license in order to get an SSL certificate. Well, I don't want to put my name attached to that out in the public. It's easier to track back to me. Well, the other thing you can do, you can compromise somebody else's box, put it up there, use their host for the exploits. Well, I'd rather not use some third party to do that. One of the great ways that available nowadays is a bunch of people doing things to bypass the Great Firewall of China. They put up SSL-wrapped proxy servers that are CGI based. So you say, provide this other URL back through HTTPS. So you can proxy things like the examples that we gave in here. We proxied the Winamp attack. We say, hey, go grab my playlist from this web server. Proxy it back through and HTTPS, and your IDS has no idea what's going on there. Same thing. There are 2 currently publicly available HTTPS proxy servers that have valid certificates, so you're not going to get the pop-up saying, hey, do you want to accept the certificate? So if you embed that inside of an iframe, and then you do a CSS attack on some other site to embed that, then you can attack people. It'll be encrypted, so if they think they're being protected by an IDS, it'll be encrypted, and you go to a vulnerable website, say if MySpace had another cross-site scripting attack, you embed that, then you send exploits across the wire, and the IDSs are completely blind.
A little bit about attacking IDS. So far what we've talked about is ways to evade the IDS in terms of application decoding, protocol decoding, IP fragmentation, things like that. Now we're going to say, okay, we want to attack this specific IDS. We want to find a way around this specific vendor's product, and there's different ways to do that. The easiest way, of course, is just flood the alert system. Find a way that you can actually launch an attack through the system, but make it so the alert that talks about that attack is either impossible to find or never triggers. There's also hardware limitations. Depending on how your IDS or IPS system is designed, you can do things to basically drain it of resources so that it can't possibly detect the attack that you're sending through it. Then there's things like session tracking. I mean, an IDS can only keep track of so many things at a time in memory, and as soon as you get over that level, you can then bypass attacks in that area. And finally, pattern matching and signature strength, where we actually start attacking the PCRE engines and the signatures and the kind of the string implementations used by different IDS vendors. So easy, attack the management system, attack the software. If you can flood the system with lots of attacks and you do a real attack through it, the user's gonna have to go wade through 15,000 attacks to figure out which one is the real one. And sure, they know something bad happened, but trying to figure out what the real bad thing that happened is gonna take a really long time, and usually enough time for you to clean up, remove your tracks, and get out. There's a specific IDS out there that you can actually trigger over 1,000 events with a single packet. So just flood that packet about 15 times and then do your attack somewhere in the middle, and there's a really small chance someone's going to be able to detect what you're doing. And finally, just attack the user. Send the attacks in a way that it's really unlikely they're going to see the attack that you sent. You can do things like trigger a whole bunch of low-level alerts. They say, okay, well, I've got a whole bunch of really stupid false positives. You send a request that you know is going to trigger a low-level alert in the IDS, but is really valid. Like, say, uploading a JPEG image where the JPEG data is a whole bunch of NOPs. So they keep sending all these NOP slide things being uploaded, and like, okay, well, this is an image that some user's uploading. It's really not bad. And then when your real NOP slide hits, they don't notice that either. So things like that. Basically, if you know the IDS well enough, you can figure out how to trigger alerts in a way that the user really can't figure out what you did. They just know something bad happened.
It's really great for things like real-time consoles where they scroll IDS events. If you can force scrolling of IDS events, like the old ISS console, where you could force it to scroll IDS events, well, yeah, run Nix or send this packet. The one packet will generate 1,000 alerts per packet. You make it scroll so fast that the Windows will eventually crash.
Or run out of printer ink. What was that? That was a great alert. Did anyone see that screenshot of an ISS console that has this Windows printer management alert saying the printer has run out of paper? And as soon as it runs out of paper, the ISS engine no longer logs because it's waiting for the Windows API to finish that call. So anyways, it's a neat attack you can do where you actually attack the hardware. In this case, the poor little printer that just lost all its paper. Let's see, where am I with this? Okay, hardware limitations. How many people have heard someone saying, my IDS can do 1 gigabit per second? Everyone loves throwing that number around. That's like, you're not a real IDS unless you can do 1 gigabit. Well, 1 gigabit's a whole lot of bits. I mean, it's a lot of bits. It's a gigabit. And out of that many, sorry, a gigabit is a whole lot of bytes, a whole lot of megabytes, a whole lot of packets. And when it comes down to it, if you're trying to if you have an IPS product and it's supposed to pass packets, you have to pass 1.6 packets per microsecond to keep up with a gigabit per second of traffic.
Oh, and by the way, anybody deploying gigabit is not going to deploy gigabit in one way. They're going to do full duplex gigabit.
Which,
and
of
so
course,
double
yeah.
it.
Now you have both cards have to take a packet in, process it, get it back out again, and now you're down to 3.2 packets per microsecond because it has to come in this side, process there, then go the other way. So unless your engine can actually process 3.2 packets every microsecond, it's not going to do 1 gigabit. And there's a lot of people build their IDS and IPS products up for standard PC hardware. There's limitations on things like the PCI bus and the PCI-X bus where you just really can't transfer that much data. If someone's using an old PCI bus that runs at 33 megahertz and they're not using like a really fast server card, it doesn't really matter what number they tell you, they're still limited to the bus speed of the PCI bus itself. Even if you're using a 100 megahertz 64-byte bus, you can only get 800 megabytes per second through that bus. And that's megabytes, not megabits in this case. So there's definitely real limits. Most people are actually only using either 32 or 66 megahertz at either, they can usually get up to 266 or in some cases up to 532 megabytes per second. But for the most part, it's about 266 and 133 is about standard. You also run into interrupt limits. Every time a packet comes into the system and it's not running in polling mode, it triggers an interrupt in the software. The software then has to go process the interrupt and process the packet and so on. You actually hit certain hard-coded limits in whatever the operating system is, whatever the hardware is, that you can't process more than 680,000 packets per second coming in on the receive interface, and you can't send more than 840,000 packets per second out unless you're using a polling mode card or using a custom driver or hardware that's really designed for this type of thing. And a lot of people selling these IDS and IPS appliances don't have hardware that can do that. If you're trying to capture 64-byte packets, each one of those triggers an interrupt, and the maximum megabits per second you can capture at 64-byte packets is 348 megabits. That's just the numbers. If you say you can do more than that, you're lying at 64-byte packets. So a little bit about realities on hardware appliances. A certain vendor uses a dual Intel Pro with 100 cards in their appliance. That's a pretty beefy Intel card. That's about as good as it gets when it comes to PC quantity hardware and network cards. They've got a 3 gigahertz Xeon processor on that box. It's your standard Dell 1U rebranded appliance. The max capture mode for that box is 760 megabits per second. That's just as fast as that hardware can go. Whatever that vendor tells you otherwise, it doesn't matter because that's what the hardware can do. Unless they've got some magic, wormhole going from the CPU to the network card, it's not going to happen. If you're in inline mode, you only get half of that because the packet has to come in one side and go back to the other side. So you only get 380 megabits per second max. And as we saw with the recent ICSA report, the ICSA did basically a rating test in different appliances to figure out how fast they really could push traffic and still do accurate intrusion detection and intrusion prevention. With the ISS G400 Preventia, it was only rated at 340 megabits, even though they sell it, I think, as a 4 gigabit appliance. So it really depends on it doesn't really matter what the vendor tells you. If they're running hardware like this and running on off a standard PC platform, there's only so fast they can go, regardless of what the marketing speak says. With any hardware, and especially with dedicated appliances, where you have like custom processors, FPGAs, that type of thing to speed things up, you've got what's called the fast path and the slow path. The fast path is what basically never reaches the management processor of the system. If you've got a router like a Cisco router, most of it goes through the fast path. The fast path comes in one interface, matches a little rule. If it doesn't match that rule, it goes straight back out the other interface. It wants to push packets as fast as it can. If you can trigger some kind of exception, or anything that requires any kind of processing by the management CPU, it goes into what's called the slow path. The slow path, it goes straight through the management CPU, and the CPUs on these boxes really aren't that fast, mostly for heat reasons. If you have a really small appliance or a Cisco router, that thing's either running like a small MIPS chips or PowerPC chip or some kind of x86 chip that's just really not clocked that fast because of thermal considerations. So if you can find a way to consistently trigger exceptions or consistently trigger the slow path on a box, it doesn't matter how fast it can process on the fast path, that little CPU just can't chunk that much data. A good example is management services. If you take an IPS appliance and you start flooding the web UI, just the built-in Riata web service or MRATA, depending what operating system you're using, whatever built-in web service it has, just pound it with Apache Bench and then try to pass traffic through the fast interface. A lot of times you'll see a massive slowdown on how many packets per second it can process just by hitting the management interface at the same time. You don't really have to do anything but do GET requests, and that's using up enough CPU that if there's any kind of exceptional condition like fragment processing, it runs out of CPU and you resource starve the box. Another interesting thing about hardware development if you're building custom appliances is something called a core. If you license a certain chip, oftentimes the vendor will also license certain cores for it. The cores are different software modules that you can license for that chip to do a specific task. So you're trying to build an appliance that does firewalling and NAT and routing and all these other fun things. Whoever you go to as your vendor for it will say, okay, well, you're using Altera or using Broadcom or using Intel. We'll sell you our cores for $5,000 for the license for all this or whatever it happens to be. They'll sell you a switch chip or a switch core, and that does switching. Another one does something else. Well, because so many vendors using these cores, they become a really good target for doing things like resource attacks, denial of service, and otherwise trying to find vulnerabilities in these cores themselves. So if someone gets access to these cores, say you work at a company that's doing custom hardware development, and you get access to these cores and start auditing them, you can find really interesting bugs that apply across multiple vendors in terms of resource starvation and vulnerabilities and fragmentation issues with these cores. Memory allocation is another issue. If you're working on any kind of appliance through IDS, you don't want it, standard malloc doesn't apply. You're not going to say, oh, another packet, let me malloc some bytes, because the overhead of doing that isn't worth the performance hit, really. What you end up doing is creating static buffers, or what we call buckets, that are the maximum size of whatever packet you're going to put into that buffer. So the packets between a certain range, like say 1 and 128 bytes, you'll put into the 128 byte bucket. And then it's in a certain one, you'll do the next set, the next set, and the next set. So what you can do is actually flood a system with various size packets close to those, modulo 2, power of 2 boundaries, and you can find ways to allocate all the buckets in a given group, make it run out of memory just by sending a really small amount of data. So, for instance, the maximum size of an IP packet is 65K. So if you send anything over about 2,000 bytes long, it's going to have to use the biggest buffer possible to allocate the rest of that packet because it thinks it's fragment has to put it back together again. So you can use up all those buffers real quick. And then you go to the next one down, the next one down, the next one down, and then you flood the system, then you do your attack, and it can't process it fast enough and it has to pass it through.
So one of the other things that you can do is you can attack the IDS tracking of streams and fragmentations directly. So one of the things you can do is you get a large number of IDSs do use hash tables for lookup tables of where packets are coming in. Crosby and Walsh released a paper not very long ago talking about attacking hashing algorithms with hash collisions. So a very popular IDS implemented how they were hashing TCP sessions with a very simple hash. The way they calculated the key was they XORed source IP and desk port to get their key. Well, unfortunately, there's a large number of IPs, 2 to the 16th, number of source IP, destination IP pairings that hash to the same value. So you can set a large number of distinct IP port pairings that hash to the same thing. And once you actually get inside inside that hash key, everything inside of that was a linked list. So you could force a walking of a linked list. So in their paper, they released for a certain broken IDS for a single PCAP of a number of 65K packets, they were able to process, make the IDS take over 43 minutes to process each packet. 43, like I said, 43 minutes is way less than 3.2 milliseconds.
Yeah.
So one of the other things you can do, a number of IDSs, both hardware and software, implement what's called a splay tree. So they used a self-balancing binary tree to store all the different states that they're handling. So they didn't want to have the problems of hash collisions. So they used a splay tree, which amortized the cost of balancing the tree across the time. So what happens in a splay tree is the most frequently used nodes are bubbled up to the top of the tree. So the person on your network who's talking the most is going to be at the closest to the top of the tree. So it takes the least amount of time to search for them. Unfortunately, because it's amortized across time, you could force it. Well, the worst case scenario is ON, so to rebalance. So we have a nice demo of attacking a splay tree. All right, so I went ahead and used the UBI splay tree, which is what a number of the IDS vendors are using. So it's a very simple splay algorithm. So, and I wrote a very simple splay tree implementation. All it does is it takes all the inputs that you're sending and insert into, Yeah, sure. Yeah. Is that any better?
Bigger, lower, bigger? Okay. So you look like a Commodore 64 here in a second. Is that better?
All right. Like I said, it's a very simple. It just inserts into the tree everything on the command line. So like I said, and I print out every time that you splayed that the tree doesn't rotate. So it takes when there's a rotate action, it prints it. So one of the great things I have a. So if you just make it do 1 through 1,000, so insert 1 through 1,000 into the tree. It does a number of inserts, and you see it print whenever it does an insert. So I'll do a grep-c rotate. This will tell me every time that it rotates, so it does a move inside of the tree. So it does 999 rotates. So okay, yeah, every time I do an insert, I'm saying, take this and put it at the top. Makes sense. Well, the great part is, so the worst case scenario for a splay tree is if you do the same thing multiple times. So if I do 1, 2, 3, 1, 2, 3, I see that I rotate multiple times when I insert the first one, or when I insert the second one. So what happens when we do 1 through 1,000 and 1 through 1,000 again? So we see a large number of rotates in here. I'll go ahead and pipe that to the grep. Actually stress again, rotate. We know we inserted 1 through 1,000 2 times, and now we have 5,000 splays. So what we've essentially done is we made the IDS reorder the tree over 5,000 times for 2,000 inserts into the tree. And actually, it's 1,000 inserts and then 1,000 lookups. Well, if you can control the network and you can control the data that's going past the IDS and enforce it in a certain order, and then enforce that order again, you can cause a worst case scenario rebalance of the tree on demand. So, and if that's happening live and the IDS is having to queue packets in their buffer, well, the splaying takes a large amount of time. The larger amount of time that you can make it splay, the more time it's going to spend splaying, the more time it's going to take, and it's going to eventually drop more packets. And if they're in an inline mode, a number of hardware vendors that are implementing splay trees, if you take too much time to process a packet, it says, okay, go ahead and pass that through, because it must be valid because I'm stuck and I don't want to drop the session. So a number of vendors handle that. Otherwise, you just drop the packet and you can make the IDS just drop the session. And a number of IDSs that are implemented in IDS mode have what's called session pickup. So if they know this session died, so they just drop it. Well, if they see a session start up in midstream, so say they turn on the IPS mode. Well, if a session was already in line, it was already starting, you were already doing your communication, well, they will continue. They will say, hey, this session's already valid, they're already doing something, I'm just going to let it continue. Well, if you can force the IDS to drop the packets, so it says, hey, this session's now dead, and then the next time the next packet comes in on your session, it's going to say, hey, this is a new session. I'm going to go ahead and let this through. If that was midway through your attack, you've now just bypassed your IPS. So one of the other things you can do, you can attack the pattern matchers directly. So most IDSs are implemented with some sort of string matching. So there's a number of ways you can attack the pattern matching. The first one is you can find the most expensive operation, make it repeat it over and over and over again. So if there's a broken rule that does something really bad, force that to happen again and again and again. The more CPU time it takes, the less time it's processing all the other packets. So if your valid attack is sitting in the queue waiting to be processed, again, like I said, a number of IDSs, if it figures out it's going to start dropping packets, it'll just pass what it has in its buffer because it needs to catch up. And again, if you can trigger exceptions, it's like we said before, if you're using PCRE for your stuff and you have PCRE compiled for Unicode, if you have FF or FEFF in the string that you're sending through, the PCRE is going to say, hey, that's an invalid character. I'm going to stop processing it. And I'm going to say it's not a match. Even if somewhere further in the string is the evil stuff that you're looking for, the PCRE, if it's compiled with Unicode, is going to say, hey, stop. This is not bad. And it's going to continue on. The IDS will let it pass straight through. Then, again, you can get into things like recursion. If they implement recursion in their regular expression engine, you can trigger that. And the other great things, you can inject termination characters. If they handle new lines differently, they say, hey, look for this up until the new line, and the server implements new line checking in a different manner. You're going to attack the pattern matching directly that way. So an example pattern matching that's implemented in an IDS currently shipping today is what you see now. It's a very simple search. So what it's doing is you have your packet data that's coming in, and you have your string that you're looking for inside of your packet data. So what it does is it walks through the packet and says, okay, at this byte, does this string match? Moves forward a byte. At this byte, does the string match? Well, so the example how you would use it, you'd say, hey, search for data, which is this size, for the string, the evil foo bang, which is 8 bytes. So how do you attack this? You maximize the work that search function will do. So if you send evil foo does not match evil foo bang. So if you send evil foo times 8, what that's going to, when you look at it, there's going to be 48 different calls to memcopy. Depending on the implementations of memcopy, you can have between 96 and 388 actual memory operations for reads and compares, which evaluates to, on a 65K packet on a 3 gigahertz box, it evaluates to 200 milliseconds for a 65K packet of just evil foo without the bang. Again, forcing the IDS, like we said, you had to process like 3.2 packets per millisecond. Well, with one packet, you can make it take 2,000 milliseconds. Again, cause the IDS to stop. It's spending so much time handling this single packet. All the other ones in its queue, if it's in the let it go through. If I can't keep up, they'll let on that through. Again, this is all dependent on platform alignment and the libc implementations of memcopy. But there's an IDS currently shipping today with this search algorithm. So one of the other things you can do, a number of IDSs are using PCRE, both in hardware and software. PCRE has a number of implementation issues that have to take into account. So one of the IDS rules that's currently shipping today on a certain IDS is looking for a from where they don't have an ampersand within 655 bytes. So what is this regular expression? For those of you that don't understand regular expressions, this is what it does. So you see the dot star. That says match any amount of data, as much as possible, up until from. And then you say, I want to match from equals. So yeah, simple, that should be self-explanatory. The next part is, I want to see at least, if I see 600 or 165 characters that are not ampersand in a row or more. So if you see more than 165 characters and an ampersand. And then, so what it will do, it'll process that data over and over and again. So how do you force the backtracking? So if you say from equals over and over and over again, and then every 165 bytes you insert an ampersand. Well, none of the froms are going to match, but the regular expression engine has to check every single from equals to, scan forwards at least 165 bytes, and look for an ampersand. If it doesn't see an ampersand, it says, okay, now go to the next from. Well, if you insert a whole number of froms, you can make that take forever. We'll go ahead and do a quick demo of that.
that particular signature is looking for a HTTP URI request where the from parameter is longer than 165 bytes. So just to put it in context, that's just a GET request.
Right.
You can do that with any telnet client if you type it out.
All right, so we're going to go ahead and take this regular expression. So great tool for those of you writing PCREs. The guy that wrote PCRE has a tool called PCRE test. You evaluate a regular expression, and then you can provide data to it. Well, there's a timing mode for it. Is -t. It'll tell you how long it takes to process. So normally, what will happen is if I just do from and then ampersand, it'll tell me how long it took to execute. So if I did the from and then an ampersand, it responds in less than a millisecond. So that's okay. So what if we do the worst case attack? So go ahead and cut and paste this. And we'll wait and wait and wait and wait and wait and wait some more. Unfortunately, the guy who implemented PCRE test didn't think that any regular expression would take more than a millisecond to respond. So his accuracy in his calculation is kind of slow, or it's kind of wrong.
So that's definitely greater than 3.2 milliseconds.
Right. And again, this is on a simple GET request. And you can, very simple, go modify Apache Bench to send this going across your wire. You can send thousands upon thousands of these a second across, a 10 megabit IDS and make, they take 5 or 6 seconds per packet instead of, 3.2 packets per second.
And this is a NetScreen IDP appliance, just in case anyone's wondering which appliance you can hit with this.
Which one's the presentation? All right, and then again, one of the things you have to do is you can attack the signatures directly. So again, how does the IDS handle something differently than the end host? So one of the things that's really interesting to handle. So very recently, Snort had an evasion announced in it. How it was handling. Had an evasion in it for how it handled spaces in separating a URI. So between the GET and then the actual URL. So the /CGIBNPHS. So the way it handled spaces was it looked for a space, and depending on what configuration you had for the HTTP inspect, it would look for a tab instead. Well, unfortunately, IIS also supported for the specific IIS version that was released publicly with the advisory, also supported tabs, new lines, a vertical feed, a horizontal tab feed, and then a control feed, or just regular spaces. And then how they handled the new lines was also different. So a number of different web servers also supported just control the /r instead of both just /r/n.
A quick thing on the isspace issue. The reason why isspace is such a big problem is that every Apache server out there supports all these different forms of space characters, and Apache also will basically eat any white space between the beginning of the method, the URI, and the version. And there's no real limits on that besides the maximum request of the entire request buffer. So if you actually pad this out with 256 bytes of random space sequences made up of that character set between the GET request, the URI, and then the version, you actually bypass, I think, 4 out of 5 IDSs I tested using the same string completely. I know I've tested Tipping Point, I've tested probably an older version of Snort, I'm not sure what the current status of that is, a NetScreen, IDP, etc. But basically changing all of the attacks that I work on at my day job to use this type of space padding, bypassed 4 out of the 5 IDSs there, and the last IDS noticed, hey, something's really screwy and dropped it, but it didn't drop it because of the spaces, it dropped it because it just looked like a bad packet.
And then the other thing you can do is if they're using something, a number of the public pattern matching APIs have limits. So for example, the from example that we gave, the attacking PCRE directly, well, a number of the IDSs use things that say, hey, if I had too much recursion, stop processing it and say, okay, it's good, let it through. So if they, how much malloc data they're going to malloc before they say stop and processing and go through. Well, a number of them are set up badly. So when they hit their max limit, they just stop processing it. So there's a certain IDS vendor that publicly right now, if they recurse more than 7 times, they say, okay, I'm spending too much time processing this, just let it pass.
So add a quick prefix to every one of your web requests, and now every one of them bypasses that IPS. kind of a neat thing about doing signature discovery is trying to figure out what signature a vendor has for a specific attack. And you start off with saying, okay, here's an exploit I know of, now let's change a byte, now let's change another byte, now let's make this byte bigger, longer, change spacing, change padding, and so on. And you can actually create kind of a black box signature detection tool for any given IPS or IDS products. And if you have an IPS, it's great because you know whether it detected or not based on whether it dropped the attack. So it's really easy to say, yes, it blocked, and no, it didn't block. You don't have to actually pull the event engine, anything like that. So a nifty thing you do is basically disable the block mode or enable the block mode in the IPS, make sure there's no anti-flooding or rate limiting stuff set up in the IPS, and basically to start permutating each character in an attack, starting from the left to the right, and then from the right to the left, and then doing both at once, and you can find out exactly what the minimal chunk of the data you're sending matches as a signature. So it allows you to basically extract the PCRE or the regex from any signature using standard kind of black box testing techniques. And it's interesting because you can also use things like hardware monitoring to figure out where the loads are. So you start sending one type of request and then slowly permutate that request different to longer or wider or different types of characters, and you can kind of figure out where the bottlenecks are on the appliance. Hardware bus monitoring, if you actually want to get crazy with a scope and actually monitor how much data is going across a certain bus, you can use that to actually figure out where the attacks are if you have a logic analyzer and take the box apart and all those kinds of fun things. Also, you can just root the box and dump the process and kind of monitor it from there, which is much easier to do in certain appliances, especially some that give you root access or protect it poorly. Finally, a lot of people are actually using encryption signatures now, or excuse me, encrypting their signatures as part of their appliance, and a lot of them aren't doing a really good job of encrypting those. So as soon as you pop that key, now you have access to every one of those signatures, and you can design an attack specifically to evade that particular IDS, that signature. So kind of a conclusion for this, our statement is basically everything can be avoided, everything can be evaded no matter what. It doesn't matter what appliance you're running, it has limits. What software you're running, it also has limits. What the attack is, it has limits. The questions really are, what layer can you evade it? How much does it cost you as an attacker to evade it? And how much time do you have to spend, and at what speed can you do the evasion? Those are really limiting factors. You can guarantee evasion at just about any IPS or any kind of security product. It's just a matter of figuring out where the balance is between, how fast does the attacker have to send packets, how much data do they have to send, and how sophisticated do they have to be able to do this type of attack.
All right. Again, our contact information. Any questions?
Yeah, we can do more demos if you want, but I figure you guys want to eat.
Yeah, because we're like 15 minutes over time.
Sure.